Hi students, now we have to discuss about AC bridges. Okay. In previous class we have to discuss DC bridges. DC bridges is used to measure the unknown resistance, either higher resistance into up to lower resistance. Okay. Wheatstone bridge is used to measure the higher resistance, and Kelvin double bridge is used to measure the lower resistance. So now we have to move on AC bridges. Why we have to go for AC bridges? Mean we can measure the some other components like inductance value, unknown inductance and unknown capacitance. Mean in DC bridges is not possible, because in DC bridges just you have to give an input supply is a constant steady state DC voltage. So in we can measure the inductance and capacitance is not possible, because inductance and capacitance having some reactance will be created, so we are not able to measure the exact value of steady state input. So then only we go for AC bridges. Okay, it's simple. AC bridges is nothing but we can replace the DC source instead of maybe we have to insert the AC source instead of DC source. Okay, that's all. Here first bridge is Maxwell inductance bridge. This bridge circuit can be used for measure the unknown inductance by compare with the standard inductance. So here we can find out the unknown inductance value with compared with known inductance value. Okay, and this is a circuit diagram. Here is the same bridge is the same. It can be formed with four arms, AB and AD and BC and CD. Okay, 4 arms are there, and we have connect unknown inductance value. This is a L1 is the unknown inductance, and R1 is the series resistance, because just maybe it is the internal resistance of inductance. Okay, so inductance is nothing but it is a coil. Okay, so here inductance is nothing but can take a coil. Okay, it is a inductance. That coil having some resistance value also. Maybe that coil will be formed with material like copper or maybe some other material. Maybe mostly we can use copper wire to form a inductance. So that copper wire also having some resistance. Okay, so that resistance here we can take a R1, and L1 is the actual unknown inductance. So we have to find out the both L1 and R1. Okay, so we have to find out the unknown resistance and unknown inductance value also. And this is connected in arm AB, across AB, and we have connect the A and D arm. That's a known resistance and inductance. So here is L2 is the inductance, known inductance value, and R2 is a known resistance. Both are variable. Okay, why these two components are variable means, if bridge is not balanced means we can adjust the resistance as well as inductance. We have to balance the circuit. So then only we have to using these two variable resistance and inductance. So here small R2 is nothing but internal resistance of L2. So here we are having the value of L1 here, and here we have to the internal resistance of coil L2 is small R2, because the coil inductance having some resistance, that resistance will be denoted R2, and the opposite arm having the two resistance will be connected R3 and R4. This is a pure resistive load. These two values are known value. Okay, these two values are known value. So here we have to connect the voltage source, DC not a DC, AC source will be connected across A and C. So the AC supply, alternative supply is given to the terminal, and we can connect the detector or galvanometer across the terminal B and D. So when the D is 0 means the circuit is balanced condition. Okay, and maybe here I have to mention the each and every component name. L1 is unknown inductance of resistor with resistance R1, and L2 is a variable inductance with fixed resistance R2. Here R2 is a fixed resistance, maybe it's also variable, maybe just you can, it is fixed with resistance mean it will be connected with series. Okay, then only I want to mention here fixed with resistance R2. So here R2 is nothing but variable resistance to be connected series with L2. Maybe this is a small R2. Okay, just you can change it. This is a small R2. It should be fixed resistance of L2. So here we have to mention small R2. So there is a small R2 here. Okay, and here R3 and R4. Maybe this is this arm BC and CD. R3 and R4 resistance should be connected here. This is a known value. This is a known non-inductive resistance. So non-inductive resistance means it is a pure resistive. Okay, this is a pure resistance. Okay, and when the circuit is balanced condition. Okay, when the circuit is balanced. Okay, when the circuit is balanced condition means the impedance across this is a impedance of Z1 and Z4 and Z3 and Z2. So here when the circuit is balanced means, why here we mention the impedance. In the previous DC bridges mean we have to mention the voltage drop across. Okay, but here resistive load and inductive load both are connected in series means, so both are resistance also drop some voltage, inductance it will oppose the current. Okay, it will opposing property, so it is like a some voltage will be dropped here. So both resistance and inductance will be taken into the account, so it should be represented as a inductance. Okay, here inductance is nothing but Z equal to root of R square plus XL, that will be inductive reactance XL square. So it is general formula of inductance. So here resistance and inductance are there, so we have to mention in the term of impedance. Okay. And here in the term of here R3 and R4 is there, here there is no inductive load, so just we can mention directly R3 and R4 is the impedance. Okay, so when the circuit is balanced, so Z1 Z4 is equivalent to Z2 and Z3. So Z1 is Z1 and to Z4 is equal to, maybe when the circuit is balanced, the galvanometer detects 0, so it's equivalent to Z2 and Z3. Z2 and Z3. This condition is when the bridge is balanced. Okay, when the bridge is balanced, Z1 Z4 equal to Z2 into Z3. So here Z1 equal to, so here Z1 equal to right, clear that. So here first we have to find out the value of Z1. Okay, just mention again, mention Z1 and this is Z3 and this is Z2 and this is Z4. So here Z1 equal to R1 plus J omega L1. Okay, how we can write that means here Z1 equal to here R1 is there. Okay, here R1 resistance, R1 plus this is a inductance. So when the inductance is present in the circuit, mean it will be indicated in the AC circuit J omega L1. That means J omega is nothing but it's a imaginary part. Imaginary part means that inductance having some opposing property we will not see. Okay, we will not see the value. Okay, that means imaginary one. Okay, because it is a inductive reactance. Okay, That means XL equal to can be found out by, that means omega L. Okay, omega L is the inductive reactance. XL equal to 2 pi FL. 2 pi FL is the general formula. 2 pi FL. That's the inductive reactance. Okay. So that is a can be represented imaginary one. That means it will oppose the actual voltage, actual input voltage. So some minimum voltage should be opposed. So it is represented as an imaginary part. Okay, maybe just you can refer the basic circuit theory terminology in previous semester you have to study it. When the inductance is present in the circuit, it will be notated as a J omega. So here L1 value is here L1 value. So then only here we have to represent R1 plus J omega L1 into, actually it is a Z1 Z4 equal, when the circuit is balanced means Z1 Z4 equal to Z2 Z3. So Z2 and Z3. So here Z4 is nothing but R4 here. So into R4 into R4 and Z2 Z3. Okay, it is a value of Z1 and Z4, and after that Z2 and Z3. Z2 and Z3 equal to Z2 values, this is Z2. So here R2. So here R2 plus J omega L2, because here inductance L2, J omega L2 plus we have to consider small resistance, maybe it consists of small resistance R2, so it should be also should be included in the value. So we are not consider that because the resistance will be internally included, so we are not mentioned here. And here it can be multiplied with Z3. So Z3 value is nothing but R3. So it should be multiplied with R3. So we can find out the balanced parameters. Okay. So comes to here. And this is R1 plus J omega L1 into R4 plus R2 plus J omega L2 into R3. And you can multiply the value. Okay. R4 should be multiplied by L1 R1 L4. R1 R4 plus J omega L1 into R4. Here R3 should be multiplied with these two parameters, and R2 R3 plus J omega L2 into R3. So here we have to get a two parameters. So this is a real part, and where the value of J omega present mean it is an imaginary part. So here we are equating the real part and imaginary part separately. So here first you can take a real part R1 R4 equal to R2 R3. So R1 R4 equal to R2 R3. We can find out the value of unknown or resistance value R1. R1 equal to R2 divided by R3 divided by R4. So here R4 comes to denominator. We have to find out the unknown resistance value. So this is the unknown resistance value R1, can be easily found out. And next one, we can equate the imaginary part. J omega L1 R4 equal to J omega L2 R3. So here J omega is a common. Okay, you can replace it. L1 R4 equal to L2 R3. So we need L1. So L1 equal to, the R4 comes to denominator here, L2 R3 divided by R4. So here L1 is to be found out by comparison of L2. So it can be found out with the comparison of L2, known inductance value. So here L1 R1 or the unknown value, this bridges may be used to measure the quantities in terms of R2, R3, R4, L2. So we can having R2 known value, R3 known value, R4 known value, L2 known value. So these are all the known parameters. We have to find out the unknown parameters like L1 and R1. So we have to find out the two unknown parameters. And some important points or important conclusion from that Maxwell inductance bridge. So here the two in the circuit is balanced means the two balanced equations are always on AC bridge circuit. The balanced AC bridge both magnitude and phase relationship must be satisfied. So here in AC circuit we can take a balanced condition, means the magnitude of voltage on the both arms should be equal, as well as phase relation. Phase relation is the same phase, okay, the same magnitude and same phase will be occurred, then only the circuit is balanced, otherwise the circuit will not balanced one. Okay, and the second consideration is we can using the value of resistor R3 or R4, because a known value can take the value of the series of 10, 100, 1000 and 10,000 ohm. Okay, you can take in the that amount of ratio, where R2 is small r2 is the decayed resistance box. So here I can connect here some resistance, variable resistance to be connected here, L2 and R2. So this is a variable resistance, nothing but we can connect the decayed boxes. So decayed box is nothing but it is a variable resistance. So we can having the box, that box having a multiple knobs are there, and you can connect the input and output here. You can adjust the knob, the inductance value will be varied, the inductance and resistance. Okay, so here L2 and R2 should be varied. So internally it should be connected serial or parallel, multiple value of inductance should be connected in the box. So you can adjust the knob, you can getting the different values of inductance as well as internal resistance. Okay, both are you can change it. And R2 is the same as decayed resistance box, and it is also having internally multiple resistance should be serially or maybe parallelly connected and combined with single box. And it can be outside having some variable knobs are there, and you can adjust the knobs, you can get a exact output resistance value. Okay, so this is a variable resistance value. Here R3 and R4 is a fixed resistance. It should be in the range of tens, 100, thousands and 10,000s, or maybe 1 mega ohm, 10 mega ohm and 100 mega ohm. Okay, that is the range. Okay, and the third important point is the balance equation enables to know two unknown quantities. The two quantities are usually resistance and inductance, or maybe capacitance. Okay, in AC bridges, only we got to find out the value of unknown inductance, maybe capacitance. Okay, so either you got to find out the value of inductance. So here Maxwell bridge is used for to find out the unknown inductance value. Maybe some other bridges like Anderson bridge or maybe a shearing bridge, it can be used for to measure the unknown capacitance. Okay, so it is measure the two quantities like a resistance, and it can be used to measure the another quantities, inductance or otherwise capacitance. Okay, and in order to satisfy the condition of balanced and for the convenient, the bridge must be contain two variables, and for the convenience each of the balanced equation must be contain one variable element only, and the equation it's said to be independent, and R1 L1 equation are independent. Okay, because the R1 L1 is independent with the remaining parameter. Okay, here R1 is independent with R2 R3 R4, and L1 is independent with R3 R4 L2. So here two parameters, two quantities to be measured, and the two quantities is independent with two other parameters, that means other known parameter. Okay, and this is a operation, and this is how to find out the unknown value of resistance value and inductance value. So now he move on phasor diagram. Okay, phasor diagram is nothing but we can represent the graphical manner. Okay, just we have to represent the operation of Maxwell inductance bridge in the form of graphical manner. Okay, that's all. So here we can take x-axis. Current I1 is the reference. Okay, I can take a reference because here we can switch on the supply. Here the current will be going through this arm and this arm. So here is I1 and here is I2. So both current are in same line. So here I1 I2 are in phase. Okay, and here first the current will be going through that one. Okay, that resistance one. So here according to Ohm's law, V equal to I into R equal to I into IR. So here I1 current will be flowing there, here R1 resistance is there, so I1 into R1. So it is also in phase of current I1. At the same time, the current I2 also here flowing through that here. So here current I2 equal to maybe the voltage maybe here the current will be flowing through that, maybe here the voltage in that ratio, so V equal to I into R. Here I2 is there, R2 plus small r2. Here two resistance are there, capital R2 and small r. Small r2 is nothing but inductance resistance. Okay, so here the both are here. The I2 is in phase with this value, so here I1 is in phase with this resistance value. And the same time here some inductance will be connected to the circuit. Okay, so here the voltage drop across here means I into j omega L, I into j omega L, I into j omega L. So it is an inductive load. So it's an inductive load. Maybe you can take a resistive load, means here voltage and current both are in phase. So it's the voltage and current both are in phase. In inductive load means you can take a inductive load. Okay, it is a resistive load. You can take an inductive load means the current will be lagging. Okay, the current will be lagging to the voltage. That means here we can take an inductive load. Here we can take an inductance coil L. So here it is a I1, because here I1 is the reference one, so it should be lagging. Okay, it's a behind. Okay, the inductance will be behind. Okay, the voltage will be behind, because its voltage is nothing but E1. So here is the voltage is nothing but here E1, because here voltage will be behind some angle of current. Okay, why means we have to connect the inductance here. Okay, so reference axis is current I1 is the reference, mean it will behind. That means it will come with back. Front means it will leading, means it will be lead. The current reference means it will lead, means maybe the voltage will be here, means it will lead. So when you have to connect the capacitive load, the circuit will be comes down. Okay, that means leading. So here we have to connect the inductive load, should be lagging. So pure because it's a pure inductive, so it is a 90 degree lagging to the our actual current. So here this line, just we have to draw the vertical line from that current line. So I1 omega L1. Okay, so here the current flowing through the I1 into j omega L1. It is a 90 degree to the actual current. And because the current I2 also here, the L2 also the same, because I2 also I1 I2 also in phase, because the same current won't be flowing through the I1 term and I2. So here it is the same. So here it is also equivalent to I2 into omega L2. So both inductive loads are 90 degree lagging the actual supply. So here E3 and E4. So here E3 and E4, that means voltage across the R3 and R4 is equivalent to the same in phase with the current. Okay, it means here because there is no inductive load connected here. Okay, if any inductive load should be connected, means it is also going for some angle. But here E3 and E4, these two arms, there is no inductive load. So the current flowing through, because the voltage and currents are in phase when the resistive load means. So here we have to connect the resistive load only. So there is no, the voltage and current are in phase. So the voltage across E3 and E4 are in phase with the our input current I1 and I2. And but at the same time E1 and E3 E2, E1 and E2, it should be lagging with some angle, theta. So here it should be draw here, it will be lagging some angle of lagging. That means it can be connected with, okay, these two arms to be connected with inductive load. So it will be lags the current, the voltage lags the current of some angle. So here it will be draw the line here A1 and A2 and we can find out the resultant voltage. Okay, resultant voltage is nothing but total voltage VE. So you can draw the straight line and you can add these two lines. So here E3 and E4, you can take this point and you can add this one, we can get the resultant voltage. We can get the, you can add the E1 and E2 plus added with E3 and E4, so we can get a total voltage. Okay, so this is a phasor diagram. That means we can represent the operation of, or represent the function of Maxwell bridge in the form of graphical one. Okay, that's all. Okay, so here everything to be draw the based on the parameter condition. Okay, so here resistive load means voltage and current are in phase, inductive load means, because we can consider that basic fundamental rules, that's all. Okay, we have to draw the diagram of function of Maxwell inductance bridge, okay, in the graphical manner. Okay, that's all for Maxwell inductance bridge.